Does it work? It seems like it's working. I'll try to move the microphone as close as possible. Okay. Ooh. So I did some changes since last time because I was eager. Wanted to actually stream all of this stuff, but I was too eager to actually look into it. So what has changed since then? x64 test. Last time I think we ended with just basic encoding, and we were missing some SIB encoding, which is the next big thing in the next big thing on the to-do list. I need to bring down the music in my speakers a little bit. Not distracting. Okay. So SIB thing. SIB thing is so for now I will just do a quick recap about what I know about these things. So an instruction is encoded in a few bytes. As we know, first byte, our most important byte that we can start with is opcode. 8 bits. Then we have, or we can even do it like this. Then we have something called mod RM bit, and then we have something like something called SIB. SIB is scale index. Yeah, I can actually align these two tabs. It will be much better. Oh, Jesus, I just did that. Come on. How hard it is to do this. Scale index and base, I'm sorry. So scale index and base. This will, mod RM, basically what it does, it encodes both arguments. So you can think of opcode as a function, mod RM as description of the arguments. Mod RM is used for some simple some simple instructions, and SIB is actually extending mod RM and adds some more addressing modes on top. And finally we have what is usually there is something called displacement, which is either 8-bit, which can be 2, 3, 4, 5, 6, 7, 8, or it can be 32, and in some cases even 64. There are some rare instructions by the manual that say in a little bit, so really visible. Yeah, so some rare instructions are there which are basically 64 bits. Displacement is technically an offset, so whatever we calculate with mod RM or SIB displacement will add a constant on top of that. So with what I found since are opcodes that actually have lower 3 bits. Good music, yeah, indeed. Hello, Rexy. Hope your head will blow up just as mine, because this is a little bit too complex, especially for Friday evening. But I'm really eager to actually do these things. So opcode, I will do some notes in here. Opcode is basically instruction code. Function, you can call it function. I imagine it like this. I will try to explain it as much as I know. And optionally, register index lowest 3 bits. So these 3 bits can be so this will be 1, 2, 3, 4, 5, and these 3 bits will be for register. Then we have mod RM. Some instructions, only some require mod RM, not every instruction. It is said in the manual whether it requires that or not. Instructions is opcodes that actually have register here. I usually don't require mod RM, or I haven't seen one yet. And I didn't go through all of them, or this is basically from push and pop to this, at least. Instructions. We also switch to markdown. So push and pop. Markdown in effect, I probably will. Yeah. So opcode, then we have the mod RM. If instruction requires mod RM, then mod RM has basically you can do it like this maybe. Then it has three sequences, three elements to it. First is something called mode. Second one, it takes 2 bits. Then we have register, and finally, I will call it X for now. This can be register or can have other specific means to MM, but generally we think about it as. I can even use this one. Okay, so we have mode, we have register, it's usually referred to as reg, and something called RM, which is this RR. So RM, something like. So this is 2 bits, this is 3 bits, and this is 3 bits. So that's for the mode RM. What it says basically, the mode has a few values. First is 0, 0 would mean that RM is used as address to memory 01 means it's the same as above, but it will 8-bit displacement follows. So that's this thing. This is same as that one, but 32-bit displacement follows. And this will follow immediately or after the SIP, but that's, and 1-1 would means that it just mean that the register in RM is used as just a register. It's just the simplest thing. Register RM is will mean that we are talking about value in register RM. So this 1-1 is used for example, like MOV, RAX, RBX. So this will be 0, 0, 0. I mean, this will be 1-1. 0, 0 will be MOV, RAX, and it's usually written like this, which means that copy to RAX whatever value is on address contained in RBX in memory. This would be the same thing, except I will use these prefixes, C prefixes, not the ones that Microsoft would use it like that, but we will do this. So that's this one, and this is yeah. So 32-bit displacement follows. This is how it's calculated. Then there are some other. This is. Yeah. Then we have this reg and RM. So RM we already talked about. However, you can have also modes like this. RBX plus, which would mean dash RAX, that we will load value and RAX into the memory. So the opposite of this one. Now, how do we know whether we mean one or second? RM is always associated with this longer expression. It's always associated with larger things. So instruction technically can have only two types of arguments. One is simple register, and second one is some kind of expression. And the expression is always associated with RM, and the simple register with the reg. The reg doesn't have anything more. So we do know that whether it's this way or this way, because these two will have different opcodes. So this will be, if I will need to check here again because I get them mixed up and I want to. Yeah, so this is MOV reg RM, it's this one. It's this opcode. And this one will be 89 MOV RM reg. But the order in the mod RM is still the same, it doesn't matter. Opcode will tell how we interpret these, but we still enter the same thing. I will use the XX. Still don't know how to do this because it's M and I don't want to use M. I can use EEE, but then I will have to write it here. Yeah. The same goes for these two. So you can technically write the same thing. You can write same thing, but with the different values of mod RM and a different instruction. So technically there is some overlap in same instructions. I'm not sure what the CPU does with these. Whether whether they have some special meaning, I don't have an idea. Because you can write it quite simply. You can have 08 8B instruction, then you will have I will write it in bytes. So we are going for this one. So this means mod rm will be 11 because we want this one. And now we can encode array-x. Array-x will be reg, so second one will be array-x is zeros. Basically, I have them. Array-x is first one, so this is 0, 1, 2, 3, 4, 5, 6, 7. So this will be 3 zeros. rbx is 1, 2, 3, 4. So it's 1, 0, 1. This will be 2, and this is 4. So this will be 1. I can split it like this, so we see the registers. So this is one version, and it would be 8b, and I will need to use this because the calculator, but I don't want to be time on decoding 4, and then there is 8, 9. Which this will be the same, but we will switch the registers, and this will be 1, 1, 1, 0, 0, 1, 2, 3. So this is E0. 8, 9. I can write it like this because I will copy it to the disassembly thing, which I have open here. We can disassemble that. Yeah, I'm sorry, it's this. We are not yet talking about 64 bits. We are talking about 32-bit registers. Yeah. So, or did I write something incorrectly? 0, 1, 2. Oh, it's 3. It's not 4. So it's 0, 1, 1, 0, 1, 1, and now this in C3, and yeah, this will be EA. Okay. This should be correct. C3, EAX, EBX. Now the other one is opcode says that we interpret these two things the other way around. And did I mess it up again? 8, 9, 1, 1. Yeah, this is completely different number. I just decreased it by 1. Oh my god! I should do this stream somewhere somewhere in the morning, because yeah. So it's the same. Yeah, it's the same thing, and I meant it's differently encoded. I meant it's encoded in these two. So you can use this one with D8, and you can write this one with C3, 8B, C3, and they are the same. That's the point. I mean, you can encode the same instruction two different ways, the same meaning, and I'm not sure what they mean by these. So they do, of course, are a natural effect of how the encoding works, but the fact they actually support them and don't give them like a special meaning, beyond me. Probably it's easier in the CPU. I don't know. I don't judge. I don't know. Simply that's the whole thing about these. Okay, so we have mod RM that we did last time, and the SIB will add additional things to it. So if you go for SIB, it has again 3 components in the same layout as mod RM. I'm missing 1 0 here. I and BBB. So it has a scale, which is 2 bits. And it's as simple as it gets. It's like 0 0 means 1x, 0 1 means 2x, 1 0 means 3x, and 1 1 no, 3x. This is 4x and 8x. This is the scale, and this is index 3 bits. That means again register. Register. And this is register. This is register, and then we have base, which is again 3 bits, and it's a register. Okay, so if we provide both mod RM and I will, yeah, if we provide mod RM and SIB, we actually get space for 1, 2, 3, 4 register. One is used as destination. In case of MOV, of course, if you are doing different instruction, then of course it has a different different meaning depending on the opcode. But if you look at it from the MOV perspective, then reg would be usually the one on the left that you're trying to assign to, and RM will be one right. And if you are loading, then it's the other way around. So you can think about this as a loading instruction and this one as store instruction. Yeah, you can see it here, like this: store to memory, and this is load from memory. Okay, the SIB will allow you to do much more with the. I will write some examples. EAX, and this will be RDX plus RDX times 8 times 8 plus and this 1, 2, 3. So this is much more complex, in much more complex expression than this one, because we are now basically what it adds is this thing. It's the indexing by and scaling up index. So you can have RCX. This is base, and the expression is, I can write it like this: is base plus index times scale plus, this is actually 2 to power of scale, 2 to power of scale plus displacement, and displacement we know that follows right after that, and it's still whether or not there is a displacement is given by this mode. Still, like you're still using mod RM. So you now see that we are using only 1, 2, 3 registers, but we have space for 4, and that's because this RM has to be switched to something special in order to for CPU to expect this SIB byte. And this special value, I don't have my manuals open, so let me try to open it. Where is my? We'll go here, projects. Oh my god, I'm missing my keys. And this is RT development, x64 resources. Yeah, I have it in the other project. This one. Yeah, so let's change document, and this will be our manual. Yeah, so we can look into instruction format, and there is here. In this section, this is what we already covered. This is the mod RM thing, and actually, yeah, mod RM, but they show it in different order. I don't know why. Let's take it as it is. And then there is the SIB byte. So there is a special value, as you can see here, for to be used by RM parameter. So if it's this one, which basically is RSP, because later you can see that it's EAX, ECX, DB, and this is SP on the same. So you will use like RSP to denote that you want the SIB byte. It's even written here, right? So it means that if we put RSP here, or ESP to be correct, value means that a SIB byte follows. If we put ESP here, then it means that the SIB byte follows. That in that moment we are losing this extra register number, and we simply just put our register in the base space here, and that's the whole idea. There are some special cases with this. You can, as you can see, you have a special case with RBP2 happening here. that's a similar thing. And there is, in case of SIB, there is also special case with RSP when used as index. You cannot index basically by this will be invalid instruction. You cannot use ESP as index register. And if you use for the base, if you use RBP, then it means these two, which is basically just indexing by EBP, except there is a if the mode would be 00, then it's just scaled index plus displacement. So this is like extraneous thing. Yeah, if you don't want to use. Yeah, so this is all covered basically in the document that I shared the last time. I can open it again because I have it still somewhere here. Yeah, I will paste it to the chat. Pasting it to the chat again. So this document basically explains all those things. I'm trying to keep it as updated as much as possible because I'm finding new things and new details about these things. For example, this only explains us how the binary operation works like mob, but it doesn't explain how the operation like push or pop work. And actually, I did kind of spoil it by saying that those have a fixed, fixed opcode, but have lower 3 bits reserved for the register. Okay, so this is that thing. That's basically all of this is already explained here, including those special things. It's kind of redundant because it copies the manual, but it's not easy to find these things in the manual. I had to go through and test it, how it works with this assembler, and for me this is much better way of storing the information or knowledge about these. So if you find it useful, whatever, you can just use it. Okay, so the SIP thing I already implemented, it already works. To prove it, let me push this thing just as a VIP work in progress thing. I will push this thing, and now okay, I don't want to remove because now I moved to something else regarding the tests, but I will just remove these bits. We'll find them in my source code eventually if I will need them. Okay. So for the SIP thing, I have kind of a proof that it works. I will have to show you how my tests are working. So my tests, I've removed them from this file, except I kept some of the special ones because there is some nuances to this process. So I started with this file where I put all my tests. So this is the same way I would write it here. It's not changed, it's just copied out here. And you can see I'm already testing the indexes here. So this is the SIP thing. These two arguments in the middle, this is the base, and this is the index and scale, and finally this. So yeah, I need a little bit because OCD works my world. Now this file is then transformed into this file automatically. It's the difference is that this is just purely calling the function, but this one actually wrapped in calling my macro test equals and calling the assembler, the x64 assembler we are writing with some arguments, and then this string at the end specifies what the result should be. So how is this done? And how do I know it should be this? Before I used this tedious process, and it was quite slowing me down. Tedious process using this website. where I would put my output from my code and check whether the instruction here is the same that I meant. If it would be, then I would do also the other tests, test whether the same instruction would produce the same bytes as I did, because sometimes, as we saw, there are two encodings for the same instruction, and sometimes, since this is using GCC, sometimes it will produce some better form of that instruction, or shorter form, for example, or a form that is informed by somebody really smart who actually tested how fast instructions are and is able to say, hey, if you do this instruction instead of this, then it will be faster. So, there are some special cases and some things that my assembler does. That also, those features are also provided by GCC, but are not provided by Microsoft Assembler, which is quite interesting why they don't do some of the things. Okay, so how does it work? How do I convert this file to this file? It uses some magic, and some of the magic is in Lua. This is the code that I wrote yesterday. And what it does basically is that this is the first part of it. It will load the input file, which is this one. Normal file load. I just have it stored in the utility library, but it's basically just simple load this file as a string. Then I would call load string and do some transformations, because this string, this is technically C, right? Lua is okay when you load C code as Lua, especially this simple one. Lua is okay with the semicolons. It's defined in the syntax. It works well. You can use semicolons in Lua. That's not a biggie. But what it doesn't know are these types of comments. Why those two comments are there, I will explain later. But they need to be there. There's no way around it. So what I do, I convert the comments to just Lua comments, and then I will wrap every number, every hexadecimal number, to quotes, so it's treated as string on Lua side. This is especially because of these two super large numbers, because Lua is not able to deal with 4-bit integers, not even speaking about 4-bit unsigned integers. Maybe LuaJIT is able to do that somehow through instantiating it in memory through FFI interface, but yeah, it just doesn't work. It was just producing garbage. Basically, this was produced this one, -1, -1 in binary. No idea. Well, idea is clear, because Lua is not meant to be a supercomputing thing. It should support the basic things, really, which is 32-bit integer, and then it has double forever. Okay, so we convert that string, this one, so it's actually parsable Lua. And then we call load string. This is Lua's own function. It's not mine function. It's Lua's standard library. And what it will do is we'll basically actually compile all this code as a Lua function into this function variable, and then I will call it. But between those two things, I will set environment of that function to my object. And this object is env, and this env object basically defines all the symbols that I'm using. So x64r, x64r, it's all there, right? I have a function for all these, for r and m, and there is also I. So r means register operand, m means memory operand or memory expression operand, however you want to call it, and I is immediate value. So I defined all those operand functions. Then I defined all the constants. So every constant, like this size constant or register constants, all are defined into the env object. And finally, there are these instructions defined, which basically defines things. So that's basically, that will pass this environment object down to down to the function. So the function will only see those. It doesn't see anything else. It doesn't see global scope. It doesn't see whatever. It will just see that one thing, that one object and whatever is defined in that object. And then it basically just runs the code. It's just the whole idea to it. And whenever the function is called, I will basically output it to my table internally here. So whenever we call x64 mov, it will return this function for this. So it will call this function, which is size, the and as. So size, this is and destination and the source. Here, like size, destination, source. Each of these arguments, these two functions, return just a string. Well, they do return technically a function, but we don't care about those details. But they basically produce a string, and finally I format all the strings together in order to produce assembly. So I will convert this file. So I can do it like this. This file is converted to ASM. And this is as close as possible to ASM, so I don't have to deal with every detail of how ML64 is parsing and what are the conventions. This is pretty much the same thing. The only interesting part of it is that it's not doing by actually implementing a C parser. It's actually doing it by reading it as Lua file and Lua code, and just defining those functions that Lua wouldn't know about. Those that will produce this out thing, which is here, this out table, and then we can go on. So we are past this point, and then we go to this point. This point basically saves a file to this path. I have this special thing going on, which is basically the save function is able to stringify this thing into a simple string, basically adding just line endings here. If it's a function, it will call the function, and whatever it returns, it feeds back to the stringify function and does it again. And you can see at this point, out contains just plain string. Every instruction is a separate string, which means it will be move AX to ECX, so on and so forth. Then I will save this file basically to the drive, and finally I will run two things. This is just setting up my environment, so the paths, this is basically my version of vars, all vars or whatever it's called, but my version, it will set up the environment locally for this process. Then it will call ML64, say where to output the object file, and that we are not linking, we just want the object file, and here is will be the path to the ASM file. And when we have the object file, which is basically a compiled thing that you can link with any executable, then we disassemble that object file into a DASM file. So this is what the dump bin call will produce. Will produce this garbage file, which is terribly formatted. It doesn't have any good structure to it, so parsing it and getting some reasonable information from it is a little bit hairy, but hey, at least we have these, so we can identify that hey, there is actually there are actually bytes and instructions here after this thing. What I do then, of course, obviously, I will just take cut off these parts from every line. If the line doesn't start with these, but it's not empty, then it means that the bytes continue on the next line. There are some like these that actually continue and extract these numbers, and that will give me the final thing, which is the expected value. So it actually goes through the whole loop of assembling it, disassembling it, and then reading whatever it wrote and what a full production level assembler is producing, and then comparing it to mine. So this will produce bytes, this will read these bytes and compare them together, and if it passes, then we go to next step. If it fails, we will call an exception, or rather, we abort the process and invoke the debugger. So I will try to run it at this moment, but I was in the middle of fixing some bugs in there. So we will get back to it really soon, and we will see whether it works. I was adding some more code here, and I was trying to find out, I guess if I remember it correctly, that here somewhere I have I think 20 on 140, and we do this. Oh, so okay, so we are loading string, and then 51 expected to close 51, and this is expected to close opening brace, opening parents on line 50. God, can already do which can do something about these streamers, like all these not streamers, yeah, but they can do streamers too. All these spammers, it's getting in. So, this is supposed to, yeah, one of these is supposed to close opening brace. Yeah. Am I not seeing something? I'm not seeing something. The A is not a function. Also possible. Format unary. Here. Function size. Oh, I know what's going on. So we get this file. And I just edit these. Yeah, so it doesn't take the size. That's why it's complaining. So the size is not there. We can say the size is 64. And just go compile it. x64 push. We have, yeah, I forgot to include, yeah, these so hey, works. So yeah, this you can see that here I've already plugged it into my build process, because my build is really a Lua file that is calling my build app and build test files that return a function, and we pass the config to it, and they will do the build. I'm using it for every project that doesn't use. So anyway, it will run the build test first, which is calling the macro assembler, ML64. It will assemble this file into object file in this build directory. So it will compile ASM to object, and then we have the dump bin launched, and that one will produce the disassembly that we then read in Lua and extract the bytes and map them back to the functions. But they are in the same order as the input file, so we know that the mapping is quite simple and straightforward. The process has some problems here, but first let me run this. Yeah, so here we can see that everything in that file, in this file, yeah, this one, first line, is the second line, and so on and so forth, and it already compared everything that, and it's all correct, everything passed, everything matched what the ML64 was doing. So this kind of works and making the process much faster. I no longer have to go back and forth between the disassembly for every instruction in order to get expected things, Although it's quite alright anyway, because you want to see that. You want to see whether it produces the correct thing or not. So you will have to, or me, I will have to now inspect these values and at least judge whether they are correct. Because we are now expecting ML64 to return these bytes and bin them, dump bin to output the correct thing, which might not happen eventually. However, for now it works, and there are some things that this process is failing at, and those are mostly features that our assembler does slightly. I don't know if it's better, but I chose to implement it in a way where I will choose the shortest possible form of the thing, because normally you can see here that I'm trying to do 32-bit mode. I'm not sure whether the size value at the start will make any sense. It makes sense for x64, because this thing then will produce or will make sure that the result is correct or we are using 64-bit register. I will show you how that is done as well. But otherwise, S32 doesn't make sense at all. And sometimes it doesn't even do that, because in this way we are asking for 32-bit, but we are passing only really tiny value which can fit in 1 byte. And immediate values similarly to displacement can be 8 or 32-bit. So if it fits in 8-bit, then I will just produce this instruction. So it's not mov EAX, which in this case would have to be, yes, yeah, it would have to be something like this, and it's much longer and will have the same effect as far as I know. Maybe there are some considerations to it, and will have the same effect as well, this will be as this one, because this is setting just the last 1 byte of RCX, which is 4-bit version of it. But we'll reset everything else in that register. So this has the same meaning as this one. And also when we do it here, I think this. In this case, it will actually produce this one, and I'm not sure why this is happening. It's B004, and maybe there is some reason why it's actually doing this. Maybe some flag somewhere. Maybe I will have to change the thing, but for now, this is how it works. So I will try to find the smallest possible thing that I can do, and I will. And also, I don't have any way of saying that, hey, I want this to be the CL. I would probably use these sizes to tell that, but sometimes we can go to smaller sizes if the operands allow it. So yeah, we will see. Maybe somebody will eventually tell me that, hey, you have to do it this way or that way. But I will find some source of problems with the way I'm doing it. Okay, so what I promised you was the 64-bit thing, and I'm not sure I will be able to do that because I've closed my goddamn file. Yeah. Okay. Yes, we will save this. Let's save this and we will do it again. So opcode molarm SIB. This is mode RR PE, and this will be scale, index, and the base. So this is how instruction is encoded, but you can already see that we have only 3 bits for registers. 3 bits means that we don't have much space for these things. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. We can only cover 8. I'm just checking whether it's really 8, so I didn't forget some value. And there is already 8 registers used. Not here, but here. This is the first 8 registers, original ones from 32 platform, and I think that is on 16-bit. But what if we want to address these? Or we want to say that we want a 64-bit memory transfer, because if you don't specify it, then or not use in assembler the correct register, then we'll only transform, only move 32. But if we want 64 bits removed in memory, so we want something like move RAX and whatever address is in RDX, and this is actually to be correct. So this is this. It says here that we want to move 64 bits worth of information from this address in RDX. Because now what it does is only this RDX. Yeah, and I found out why here we always have our registers for bit mode, because we are addressing memory, and we know that 64 bits always are can reach 64 bits of memory. So that's why on this side, whenever we are addressing memory, we are using always 64 bits there. So how do we distinguish between these two? And also, how do we do this? For example, now we can just try RX. So we have only 3 bits, so maximum of 8. How do we encode these additional registers, and how do we say that we want 64-bit variant of that? Because my API x64 test obviously always uses these 64-bit names. It never uses like a 32-bit name, which would be ECX or just 16-bit or just 8-bit. So how this is done is by prefix. And the prefix is called REX. So this is additional complexity to this thing. REX, I have already written the code for encoding it, and I'm already using it in test files. So it has this form. It starts with this value, these 4 bits, and then the rest of the bits are WRXB. WRXB. And now let's talk about what those are. Again, I'm repeating, this is me learning these things, and as I learn them, I'm trying to explain them to you. So that's all I do. I'm not expert in this, but what I found is this is operand size. This will switch between 64-bit. I mean, depends on what mode you are in, but we are considering we are on a 64-bit machine and dealing with 64-bit code. We don't care about anything else. Yes, we are using 32-bit operations sometimes because it just is faster. Because if you only need like one 32-bit number to be loaded while load, double that. That's why. Operand size, basically for our case, when we are dealing with 64-bit platform, we'll switch from 64 bits we'll switch from default, which is 32 bits, to 64 bits when it's set. So if this thing is 1, then it will switch from default to 64 bits. Okay. Default on 64-bit is 32 bit. I'm not sure. why that is, but yeah, I can see obvious reasons why that is. Then we have this R, and that's extension for our rec thing. Here, these three things. So this is mod rm rrr extension, and it basically adds that one bit, like whatever is here in this R is added here, the register in this field. So suddenly we are getting 4 bits instead of 3 for this value. If you go next further, X is extension of SIP index. So with extension for this one, so it's the same as whatever you do in X is extension for that SIP index thing. So it will give us a possibility of 4 bits per index, where we can obviously then use the extra 8 registers. And finally we have this B thing. This is what I just learned. Extension of mod rm, which would be mod rm is this one. And I think, no, mod rm is the last one, is EEE. Mod rm extension. But usually we have, when we are using SIP, this is RSP, as we saw last time. Register. If we are not using it, then we can extend it through here, through this, and it also extends the SIP base. So whatever bit is set here is set also here. So if this would be RSP is 0, 1, 2, 3, 4. That's the one. This. So if we set E to 1, then it will be this thing. And suddenly, if we extend it, it's usually written like this. By this 1 bit, this is RSP, and this becomes R12, right? So now this is a completely different thing, right? It's not RSP, it's R12. And it turns out that here CPU only only thinks about lower 3 bits. It doesn't when it's detecting whether it's RSP or not. It's only thinks about those 3 bits. It doesn't take this into account. If it's something else than RSP here, then then it does read this extra B from here. So that's great, right? This is basically for base. Yeah. So that's the idea. But every specialty that applies to RSP case in your code also applies to R12 case. So if you look into this code, you can see that I'm already doing that. Like, it can be RSP or it's R12. I could just easily do this here, right? Like filter out the thing, but I wanted to be like filter, leave only lower 3 bits. But I wanted to be explicit here because I would like to be able to read this code in a month or two, and I didn't do anything with it. And same thing goes for RBP, which is the next register. So this is 4, this is 5, and whatever applies to RBP in terms of exceptions applies to R13. That's like a price we have to pay for this kind of schema and extensions and shit. Okay, and yeah, and that's basically the idea. So whenever you want to use these extra registers, or you want to extend one of these, yeah, which means that you will have to extend one of these 3 things, or you want to force it to transfer 64 bits, like say that operand size is now 64 bit, so don't produce EAX but produce RAX. You have to provide this extra byte before the entire thing, before the entire instruction. So it means that simple instruction can have up to 4 bytes plus displacement, which can be up to 64 bits. It's quite a lot of data, but hey, as long as one understands it and as long as it works, I'm okay. It's not the worst thing I have ever seen in terms of encoding. It's still quite alright. Yeah, sorry, a little bit of work thing. Okay, there is a little bit more information to this, but we will get to that. So that's how we switch between 64-bit and extra registers and 32-bit and just the basic registers. We use this extra thing, and we can see that it usually starts with a 4 at the start. Yeah, this one, for example, this will be the thing. X prefix. Okay. So then, when I had these 64-bit versions done, I've actually went and implemented the pop and push, which are a little bit different to MOV. First difference that comes to mind is that they are not binary, they don't take 2 arguments, but they are unary, they take just 1 argument. And here we are. So this is how I define instructions now, or opcodes rather, for instructions. I have this simple structure of binary. Yeah. And it has 4 possible values for now. Probably it will need more, I will see. But the code, the assembler below will basically choose, based on what the operands are, it will choose one of these opcodes. If that opcode is set as 0, it will produce an error. So we wouldn't be able to use that expression or produce code. Then for unary, it's kind of the same deal, except it doesn't encode 2 arguments, but just 1. I'm not sure I will need whether unary can take memory address. Not sure, we will see. I kept it like in a similar format for now, but probably won't be needed at all. Not sure if it can take it. Yeah, it can take immediate value. Yeah, that's correct. And then for pop and push, those are defined as unary and have only one variant for now implemented, and that's the variant that takes register. And now I found these two to be quite interesting, because even though they this is the opcode for push and this is the opcode for pop, and how do you do that? How do you encode which register you mean? And in these cases, you type kind of easily visible on this 58 one, where you see that the lower 3 bits are 0. And 50 also has it, but it's not as visible there. There is 4 bits zeroed. But these 3 lower, I'm not sure how you can see these, but it's this kind of a deal. That the opcodes, some opcodes, at least for this push and pop, I haven't looked further, have used those 3 lower bits. But now the question is, how do you extend it? Like, how do you specify R8 register? And it's quite simple. You again use this rex thing, and you basically just say on the upper register you will say 1 here, and that's it. So suddenly one simple opcode for push or pop is twice as big. That's the idea. So this is opcode register extension. So this is like a second part, second way of how to encode those things. First way is opcode is fully set and you have to provide mod RM and or SIB depending on what addressing mode you want to use, or the opcode already contains space for a register field register in here, and you encode the register there. In all cases, you need to use rex if you want to use switch to 64-bit mode, or extend this thing, or any of these RREE, IIBB things, and that's kind of a whole idea for now. So this covers the whole set of instructions. I hope that like this is the whole fucking thing there is. Like there is a no another specialty to it. There are of course instructions like that take no arguments at all, but those are quite simple, right? You don't have to do any kind of logic behind it. You just return it in this inst object, which is simple. It's just static or fixed buffer of bytes. Count will be, so you return 1 byte, count will be 1, and this is for me to announce error. It happens. I'm not sure how I will be dealing with errors yet, but I just store it here because it's returned from every of these. Okay, so that's the whole idea. So you have binary and or we have binary, we have unary things, and we can do defining a new instruction, basically just these things. It's just writing down mapping to these 4 opcodes, or leaving them at 0 if you don't support them, and that's it. Just map it, and then I have to create this extra function that deals with it. That's the whole thing. Now what we are missing, which is already written here, is being able, because you are able to do pop and some value that can be up to 64-bit. So we can do this encoding, and you can I will save this one, test input. You can see that I have tested only pop ones and only push ones, and the generated output, you can see that these require that rex prefix, all of them, when they are using the extended register. That's the thing. And pop as well. This was for push, and this for pop. So what we want now, and we can actually try this process. We want x64 pop, and we want x64i this time. And I usually use these values. So we want to pop. I don't think it will work with pop though. We want to do it for. Oh, that's even different thing. Okay, so we will first do the push IMM 64 or IMM. So that's the first thing I want to do. This thing is a little bit different. You can pop from the stack to a memory destination, so it will be similar to pop keyword ptr arrayx plus arrayx times 4 plus some displacement, and it will take things from stack and put it on this memory location. Quite interesting, and I'm not sure what the use is for that. It seems like a copying from one location to another, like copying from stack to memory. Which stack is still memory, so it's copying from memory to memory. Our stack has a higher possibility being in L1 cache, so or high chance, especially if it's live code. So yeah, so what we want to do is this first thing, which is just pushing a fixed value to the stack. So what we need to do is to look into this manual and find out whether there is such a, I think there is already such an instruction. So we find push. There is a pop. You can see here there is RM thing. This means that if it says this, then it means that that it takes this mod rm. You have to write this mod rm byte, which means you probably some addressing code zip. We don't care about these DS, ES. First, I don't know what they are. I believe they are segmenting registers used on 16-bit machines, maybe even 32-bit machines. Not sure. I don't care about those because I only care about 64 bits. No real reason for me to care about anything else. So that's pop, and let's find push. Let's push. And this is push A and push AD. It's interesting. Haven't seen those used. Yeah, I will look for those. So this pushes stuff onto the stack, and there is, yeah, here are our values. So it allows us to push maximum of 32 bits to the stack. So if you want to, I guess, if you want to push more than that, if you want to push 64 bits, then we would have to use this version and place the value in the register first. Oh, it is what it is. And I think maybe there will be some special instruction for these. But to be frank, I don't know whether it even makes a sense. So we know that, okay, so there is IMM16 and IMM8, which probably suggests that we should, it will be happening multiple times, so we can add the version for IMM16 as well. For unary, maybe it will happen for the binary as well, and I think it will. I think I saw it with mob. And what we will do, it's push, and we will do IMM32, and I'm defining them here, which is push, and this is IMM32. I'm doing it this stupidly complex way, unnecessarily probably, but I think if you are dealing with these kinds of shits and you want some special instruction or whatever, or special version, then it probably will be handy to have like constants for opcodes if you need them. You can either use these structures, or you can use directly this enum if you want to. I'm not sure whether it will be needed, whether I should hard code it in, but I don't want to cover every possible case with this library. I want to cover just those most important cases that repeat over and over, that are hard to write. If it's simple things writing to memory, then you can probably just write it yourself. But for now, it seems like a good way how to go about the library. Okay, so the code was 6.8, right? Yeah, 6.8. This will be 6.8. We can push this one. I'm not sure how 16-bit works at all. Like, I don't have a single idea how to switch to that, because it's quite interesting to be able to move just yeah, and we can see that probably it has, yeah, it has a, yeah, that's maybe the idea, that you can switch from 32-bit to 16-bit mode, and that's why Pair originally didn't have it in like a special instruction, because it always happens that 32 can be upgraded to 64, but also downgraded to 60, maybe. So I will keep it like he had it, and we will see for how long we can do this. So IMM8 is 6A opcode followed by bytes, and this is 8 bytecode followed by double word, or in case of 16, that's a word. Okay. So this one, and then let's do this one, and this is IMM8. Yep. So then we need to upgrade this thing. There is also mem argument. So we take in the structure that we just filled in. It will have these 4 members, 4 opcodes, 4 possible opcodes, and we take in an operand, and then operand has a kind, and we decide based on the kind what kind of instruction we will choose from the set of opcodes we have, and whether we will need yeah, I will probably have to do something else on the background as well. But I will try to finish these things first, and then I will check. Okay, so IMM. So it said that it takes its opcode and then it just value. So we have to choose by the value. I guess if d.imm is lower than this one, over or equal, then our opcode will be. We can just do this as well, and it will be here. Use this op is .imm8, and if it's larger than that, then it's imm32. Okay, this will give us opcode. We will deal. This is the Rex writing, so we don't need those things. Then we do. We will output the opcode. So first thing, and maybe. Oh, maybe we can do it the other way around. We can do it like this. Of IMM32. IMM is lower or equal, else we'll do this thing. IMM8, IT++, and this is x64 and bytes. Write bytes. This is a function. Do I not have it here? Yeah, I do. So the bytes are in the IMM, which we need to cast to bytes, IMM, and we want just one, which we can just. Yeah, I will leave it like this because it just the code doesn't have to be super optimal right now. We can optimize it later. And I want to be sure that I have these things symmetric as possible, because then it's easy. So if the immediate value is lower or equal to 255, then we write this opcode and write out the immediate value. Otherwise, we think it's 32 and just write that one. And we probably will have to deal with 16-bit version as well eventually. I want to do 16-bit way later, because that's optimization for us. We are not targeting any 16-bit platform. What 16-bit will give us is technically just optimization of how much memory we move up and down, but it will work on top of existing structure. So that's it. Okay, so this should be the whole idea. So when we go here and we run our build process and the code, this should produce something meaningful. Oh, damn, yeah. Push doesn't allow, pop doesn't allow for immediate value. What does that mean? Oh yeah, and I of course was explaining and changing my code. x64 ECX, there it is. Yep, and it passed. It generated this thing. Which we can also check for this, and if we it's push as we wanted it to be, and if we assemble it, it's the same thing. Yeah, so the GCC does the same thing. Okay. Now there is a slight problem, and that's we don't have any way pushing anything larger, we would have to use, we would have to use the registry, which means that it's more complex value, a more complex process. I'm not sure whether I should do like things that produce multiple instructions, like higher level macros. But what I should do is I should protect this from 64 emit error, and the error will be 32-bit immediate is maximum. Yeah, so if you use larger value than that, because IMM here, use something larger than that, then wrong, and we cannot produce the code in here, and we need to inform the user. So that would be one thing, and we can test the smaller one as well. I'm not sure if it will probably not work with ML64, the assembler we are using, but we can try it definitely. These things usually fail there, because you have to be really explicit with that. No, it worked. Okay. So it was smart, and it encoded the smaller version of push, which is just 2 bytes when the value is smaller, and we did that as well. So that's so the optimization worked. Now what we can do is we can detect this one extra error that was happening, like using push with value that's invalid. So what we can do here is that we'll remove this one if op IMM8 and we'll just check it IMM32 and or we can detect it here. And it's not op IMM32. We can write it in here, check. This way, check IMM. Yeah, so we can implement this function that will, and we need to, that's right. So we will just give it the, I'm thinking maybe we can do this as well for 32-bit. Because we need to type it like this, we can overload in C, of course. And have a visibility. Yeah, because we can check for those two here as well, right? And it's at the same, it's like the same offset and same structure of both. And technically, we just need to say what's on the right here. So if we say what's on the right, then we know the left is always registered. But I guess this will also have these kinds of formats where you have memory location and immediate. So I will keep it like this. Probably will do it like like this, because op unary is basically the main of this structure, so I want to associate that structure with. So we will see that, but we cannot do it here. We need to test for errors in here. x64 test equals op, and we know it will be error. I'm detecting whether the bytes thing is actually text error, and if it is, I expect it will return an error. So I'll run it. Yep, and it works. And there was also the error one somewhere. Yeah, it's here. So it passed with error. Immediate values are not supported. Eventually I will have this testing for the error messages as well, but I will have to go through the messages and make them sound the same, sound consistent. Alright, so we got the IMM thing working, and tomorrow, yeah, I guess we will do the mem thing without actually spending so much time on repeating what I said or what I went through for mem. What I will probably do in the meantime is that I will try to find and define what values, what operations we want, what opcodes we need. For now I'm thinking we will need add the we will need sub, we will need ret, we will need call, we will need int3, because this will get us to the debugger. This is great if you are debugging through Visual Studio and you start your function with this or your code with this. It will immediately show you the disassemble code, and you can step through it to immediately see what's happening. You don't have to fuck around with memory and yeah. This is something good, and I think call will have multiple versions. Like what will be direct, and second one will be indirect. Direct will take like a register, and otherwise it will take some immediate address or something like that, or immediate value with the address of the function. Add and sub will be binary, so it will be DNS. Probably red doesn't take anything. Call is here. Push and pop we have. When we are heading towards is being able to write proper function prologue and proper function epilogue. So we want to be able so this is my actual language project. Close these. This is the old version of x64. That is not. Yeah, it just went nowhere. Too complex. But I have some notes in here for x64, I believe. Yeah, here it is. So yeah, eventually we will need floats as well. The prologue, what we want to support for a simple function is that we should be able to push, I think it's RBP that we need to be pushed, because we will need it for accessing stack. At least that's what I saw as being best practice. Or that's what compilers usually do, because then RBP has no other use, I think. And you use it just for accessing stack. You put the RSP value to RBP. Push RBP first. It's, push RBP. Then you, of course, mov RBP RSP, and then you can deal with the stack way, because now RBP has a stack pointer. You can use to access the stack and leave RSP as it is. So yeah, that's what we will have to do. We will need to compensate for red call in order to have stack aligned to 16 bytes. And then we will have to make some space for local variables as well, so that's why we have a sub in here. Of course, eventually when we are in the epilogue, I'm not sure whether we should be dealing with RSP at all. I'm now not sure whether it's registers to be freely used by callee. Yeah. RSP. Yeah, so RSP has to be restored back to where it was after the call. So we will have to do add as well. We want to get it back to where it was, although we can push it and pop it always. Our instruction set smaller. Epilogue just needs pop, and then we have a full call, and the call is basically just a bunch of moves and the call function, the call instruction, which will get either a register or address of the call, and that's it. That's our target with all these things. And then eventually we will go to next part. That next part will be arithmetics and floating points, looking into, because eventually I want to be able to compile a language with into x64, which is like C-level language. Will not be super optimized or anything like that. I just want to have that full circle of being able to write a bunch of code in my language and then translate it to before and see what the performance is compared to, for example, scripting languages that are normal scripting or embedded languages that are not typed, just dynamically typed. They are basically dynamically typed, not statically typed as my language. So that's the idea. I will have to go now. I would like to stay, but I'm feeling I'm really tired at the moment. So I will probably stream over the weekend as well, probably a few times, but I don't want to promise anything. But yeah, thanks guys, and see you next time.